What's up, guys? The plan is pretty simple for today. So basically what we're going to be doing is we're going to be going through the whole process of prototyping one of these lightsabers that we make, and the one we're going to be prototyping is pretty awesome. We're going to be adding in a gyroscope and an SD card, speakers, everything you need to make it like a top-of-the-line NeoPixel lightsaber with all the effects, flash on clash, everything. Hopefully we'll even add smooth swing later on. So today what we're going to do is look at the extra modules that we'll be needing, wire everything up in a prototype, and then hopefully at the end test it with a program that I've been working on. And then next time we live stream, we will go through and actually make, the final program, because what I have right now is just a test program. So hopefully we'll be able to test it so we can see how awesome it's going to be. Yeah, that's basically the plan for today. So yeah, let's go ahead and get started. All right, so hopefully you guys can hear me okay. I'm just gonna go ahead and show you guys the new stuff that we're going to be using. All right, look, if we didn't have any technical difficulties, it wouldn't really be fun. So let's get into it. Okay, so first up, we've got this MPU 6050 gyroscope. And yeah, basically this will let us see the acceleration and the rotation of the lightsaber, so we can detect if it just was accelerating very fast, that means we're swinging it, and if it just stopped accelerating or changed direction, that means we struck something. So we've bounced off that, and we want to show the flash on clash effect. We've also got this SD card reader here, and I'll link to all of this stuff in the description, once the stream is finished for you guys, and an SD card, because that's what we'll be storing all of the sounds on. We're going to be, still using, like a lightsaber blade similar to the ones we did before, though there will be a small adjustment to the blade design, which I'll explain to you guys in just 1 minute. Now, for this build, we're going to be using an Arduino Nano, and you definitely need the Nano this time, because this is a big program. Moving all the sounds and stuff around makes it a much bigger program, so you're definitely going to need the added storage space. And even then, the program space is going to be pretty tight. So I'm just going to click my Nano down onto this breadboard here, and then we'll start building out our prototype. So the first thing I do here is I would just head over to my computer, and I'd add the components. One at a time. So I just hop over to Google here, and I just search up how MPU 6050 Arduino wiring, and I just look up how we can wire this up. So I'll just click on some tutorial here, and you'll see all these helpful people on the internet have put out all these tutorials with wiring explanations for how we can wire this up and where we can wire this up. So we can see that basically the MPU 6050, and these pins are actually labeled on the module, so we can actually read it on there. But we're going to connect VCC to 5 volt, obviously, ground to ground, and then we just have to connect SCL and SDA to the SCL and SDA pins on the Nano board. Now, each Arduino board may have slightly different SCL and SDA pins, so we can just open up another tab and search for Arduino Nano SCL SDA pins. And if we just go ahead and search that, we can see right here in this description here, it says, oh, SDA is on A4 and SCL is on A5. So right away, we already know how we're going to connect the SCL and SDA wires. With that, we can just go ahead and connect up our MPU 6050. Now, the first thing I'm going to do is, just to keep everything a little bit neater, is I'm going to actually use the side rails on the breadboard. So I'll grab this orange wire and connect it from the 5-volt to the positive rail, and I'll grab this black wire and connect it from the ground to the negative rail. That way, this whole rail here has the 5-volt and ground, because there's going to be lots of devices plugged into each of those. All right, so then we can go ahead and take wires from there to, and from the Arduino to the MPU 6050. So up on top we have the VCC pin, and that's first. Connected to the power. Ground pin is second. Connected to ground. And then we just looked up, you can always double check. SDA is on pin A4 and SCL is on pin A5. So SCL goes to pin A5. And SDA goes to pin A4. All right, now if we go ahead and power on our Nano, we should be able to see that the MPU 6050 goes ahead and lights up. So we've correctly connected the power, and we've got the other wires connected as well. So the next thing we want to add is our SD card reader, and I've already looked up all this information, so we don't really need to go through that process again, but you just do the same thing as you did for the MPU 6050. So each of them is going to have the VCC and ground, so we can just go ahead and knock those out, connecting them to our rails, which we went ahead and powered. So I'll connect this orange wire to VCC and this black wire. Go ahead and connect to ground. Yeah, there's no lights on this one, so don't worry if it doesn't light up. And then this one connects over SPI. So we have MISO, MOSI, and SCK, as well as the chip select pin. So the first three of those are, once again, dedicated pins for the Arduino Nano, and it'll have its own specific pins that are supposed to be MISO, MOSI, and SCK. And the last one, the CS pin or chip select, is something we can set in the code, so we can connect it wherever we want. So if we want to, we can just go ahead and look this stuff up once again. I'm just going to go ahead and search for, let's read the, why don't we just go ahead and search for SD card reader Arduino. No, actually, sorry about that. We just want to search for SPI pins Arduino Nano, because we already know it's connecting over SPI, and we just want to find out which pins the SPI pins actually are. And here we go. We've got 11 is MOSI, 12 is MISO, and 13 is SCK. And this person's gone ahead and used 10 for a chip select, so we can do that too. It doesn't really matter. We'll set it in our code anyway. So let's go ahead and add that. Once again, that was 11 for MOSI, MOSI. 12 for MISO, and 13 for SCK. All right, and then the last thing is just to connect the chip select pin wherever we want, but in this case, we're just going to go ahead and do 10. Just to keep all of those connected in a row there, so they're all in the same area. All right, so once we have our SD card reader and our gyroscope in, we need to add our speaker. Now, I'm just going to be using this random speaker because my speakers actually haven't arrived yet, but you can definitely pick up some speakers that are more, round, that fit nicely in the lightsaber hilt for your own lightsaber build. So the black wire, we're just going to connect to ground, but then the red wire, what we need to do is we need to not just send sound signal to the speaker from one of the Arduino's pins, we actually need to amplify it. So the Arduino's pins don't have that much power going through them. So we're going to amplify it with the standard 5-volt rail on the Arduino to make sure that it's the maximum power the Arduino can supply, so we get the maximum volume out of the speaker. So in order to do that, we're just going to need a few pretty simple components. And the main key here is our transistor. Now, if we go ahead and take a look at it, what I have right here, you can't see it very well on camera, but what I have right here is an SS850 transistor, and basically the way it works is it has these 3 pins on it. Hopefully you can see those, and we can connect the power that we're supplying to one of the pins, and then the control to another pin, and basically it'll allow us to use the Arduino's pin as a control and the power from the 5-volt pin as the power. So we'll be amplifying that signal to the speaker. So I'll go ahead and connect it to the breadboard. And then we're also going to want a resistor which will go between the signal and the central pin on the transistor. So we'll be sending the signal from the Arduino. Let's do pin 9. We can do whichever one we want, but again, it's nice to keep them in a row. And we'll be sending that through this 120 ohm resistor to the center of the transistor. Then we want to supply the power from the 5-volt rail here to the left side of the transistor. And then we're going to read, with the speaker from the left side, of the transistor. So we've got the data going in the center, the amplification from the 5-volt rail going into the right side here, and the speaker going into the left side. So we're amplifying it using the 5-volt pin. We're amplifying the signal into the speaker to get out just a little bit more volume. All right, so that's all of the new components, and we can slide this SD card into the SD card reader. But of course, we also still need to connect the blade and a button for, controlling things. So let's go ahead and connect those up. All right, for the button, I'm just gonna set this button in the middle of the breadboard here. Let's just try to neaten things up a little bit. Hopefully you guys can see what's going on. We're going to set this button in the middle of the breadboard here, and we're going to wire it up. So we want 5 volts from the 5-volt rail going to the bottom right side to power that up, and then we're going to take the signal from the top left side here, and it'll only reach so far, so let's plug it into port 3, digital 3, and then we're going to want to connect the plug for our lightsaber. So I've got one right here. As you can see, it's the same plug as last time, just one of these female LED strip plugs, and we'll connect the green wire to port 4, which is where our data will be coming from. We'll connect the white wire to the ground rail that we already set up over here. If I can manage to actually get it in there. And of course, we'll connect the red wire to the 5-volt rail that we also set up. I've gone ahead and extended it with this dark tan wire just because I tin these wires to make it easier to plug them into the breadboard, but sometimes once they're tinned they get a little fat and hard to fit into the breadboard, so I just went ahead and tinned them. Alright, so we've got our speaker, we've got our SD card reader, doesn't want to stay face up. We've got our gyroscope. Let me go ahead and put it right side up just so that we don't get any false inputs. And we've got our button, and we can go ahead and connect up our blade. Now, as I mentioned, we will want to make a couple of adjustments to the blade over the blade that we were using for the last lightsaber build, just to make things more efficient in our Arduino program. But for now, let's hop into the Arduino IDE and see what we can come up with in terms of a program for this. Oh, we got a question in the chat. Let me switch over. You guys, we're back at the computer, and yeah, so pretty much learn to code just following tutorials just like this by people who make tutorials. There's a number of great resources out there, like How To Mechatronics and stuff. And yeah, they all have lots of awesome resources. They really know their stuff, and they make it, some of them make it very easy for you to learn this kind of programming. So that's what we're going for here. And let's try to hop into our IDE and figure out some programming for this thing. Okay, so basically, what we're going to start with, this kind of little, cheating from the program that we're going to build in the future, but we're just going to start from a new sketch, and we're going to try to build out the features of our lightsaber, just the way we would when we're figuring it out for the first time. So you'll be able to find sample code for each of the different components online, and then all we have to do is say, hey, let's take the SD card sample code, let's take the gyroscope sample code, let's take the LED sample code, or in this case the code that we created for the last lightsaber, and let's mesh them all together into a program for this specific lightsaber. So most of the heavy lifting has already been done. People have already got the libraries and everything for us. It's our job to just figure out how to compile it, and that's what I'm going to try to show you guys in this video here. So the first thing is, let's check out well, first, obviously, we need to install our libraries. So we're going to need the MPU 6050, and we're just going to want the Adafruit MPU 6050 library right here. As you can see, I've already downloaded that. So we're going to want that. We're going to want the SD library, not that one. It's just this one, SD by Arduino and SparkFun. And yeah, it just works with all the different varieties of SD cards and just allows you to read from basically any SD card reader, any of the ones I've ever used. So we're going to want to download that. And if you don't have it from the last lightsaber build, we're obviously going to need the fast LED library. You can see that right here. And I think that's about it. Anything else should be just dependencies of those libraries, which should get automatically installed. If the IDE asks you, hey, this library has these dependencies, do you want to install them? Then say yes, because it needs those dependencies and it'll auto install them for you. It's very handy. Oh, one last thing is we need the TMR PCM library. This one you'll have to get online from GitHub. So if we just search for TMR PCM Arduino, it seems like a good thing to search. We can pull up the Arduino reference, which will just take you to the GitHub page, which is where we want to go. And then if we download this zip file, then you'll be able to add it, going to sketch, include library, add.zip library, and then you can just add that library. That's the speaker driver library, so it's the one that turns our sounds into stuff for the speaker. And speaking of sounds, what I've set this up to do is we have all these sound fonts online for the different lightsaber boards that are already out there, like Profi or Asteria. So what I've gone ahead and done is I've made our program work with the Asteria board's file format. So you can see if we were to download one of these sound fonts, I've got a couple right here, and I'll link to some stuff in the description if you guys want to check out how to get some free sound fonts. But here is a sample sound font, and you can see they have these different formats for the different boards: Profi board, Xeno 3 board, Asteria board. And so I've made our program to work with the Asteria board's file formats. So you can see we have all these different sounds which other people have gone ahead and made, and they sound really good. And these are the sounds that we'll be using on our lightsaber. So we've already got, a few different clash sounds, which we'll randomize between. We've got a hum sound, which will just be constantly playing. We've got some swing sounds. We've got obviously the activation effect and the turn off effect and all kinds of good stuff. So if you download any sound fonts, then it'll usually be laid out like this, and you can just take the Asteria folder, rename it to whatever the sound font is named, and that's what you're going to use. Now, there is one other thing you need to do. Unfortunately, the Arduino boards can only play sounds of a certain quality. So if we look at these sounds here, we can see that their sample rate is 44.1 kilohertz and their bits per sample are 16. That is too much information for the Arduino to process, because that's a small brain. So we need to actually adjust that. Now, there's this free program you can get called Audacity. You can just search up Audacity on Google, and you can download this program. It's a sound editor, lots of features, but we only need a couple. The first one is, and this is Windows and Mac, so you can do the same thing either way. The first thing we want to do is go into Preferences and change the project sample rate to 32,000 hertz, which is the maximum that the Arduino can understand. So we're just decreasing the sample rate so that the Arduino can actually play this. Then we're going to want to go ahead and export it, because it needs to be a WAV file, and it already was a WAV file, but it was too high quality. We needed to say unsigned 8-bit PCM here. So if it's one of these other options, select unsigned 8-bit PCM. So you have a WAV file with only 8 bits, and then you can just go ahead and select the folder where the stuff already was. So here it was somewhere in here. Yeah, here we go. It was in this hum folder, and it's called hum1.wave, and then we can just go ahead and replace it. So we're just going to replace it with a file that has slightly different settings, slightly lower quality settings, so that the Arduino can play it. And as you can see here, now it's gone ahead and changed it to 32 kilohertz and 8 bits per sample. And yeah, now the Arduino will be able to play it. It's a little bit tedious to go through all of these, but it's just what you have to do for now until unless you have, an Arduino board with a slightly faster processor, which would be able to play these higher information files. So for now, yeah, just download Audacity, go through each of these files, open it up, and change it to 32 kilohertz and 8 bits per sample, just the way I showed you. The other thing you can do is I'll just go ahead and release these files that I've already modified, so you don't have to go through and do all of that grunt work. So if you want to download those, I'll put them up so you guys can download them later. Yeah, but for now, I've already gone ahead and copied this Asteria folder just like this. After I made all the edits, I went ahead and copied it onto my SD card, and I renamed it to Galaxy. So, because it's the Galaxy's Edge sound font. So I just renamed it to Galaxy. So it's basically on the SD card, this is what it looks like. It just says Galaxy, and then it has all these folders in here with all the files modified just the way I showed you. So that's what's on the SD card. That's what you can put on your SD card. And that'll allow you to have all the sounds nicely formatted for your SD card, so you can play them just like that. So since we have all those sounds, let's go ahead and set something up so we can actually play those sounds. All right, so if we head back over, this is actually the TMR PCM library, which we downloaded. And if you notice, almost all of these libraries now show up here under the examples tab. So if you go to File, Examples, then you can usually pull up examples for whatever library you downloaded. So here we can see TMR PCM. Let's try Basic. Let's see what's in here. And yeah, you can see this actually, this looks pretty good. So you can see they defined the SD chip select pin to 4. Now we connected ours to 10, so let's just go ahead and change that to 10. And then here is where it's telling it to play a sound file. So it's trying to play the sound file music. Now, obviously we don't have that. So if we go ahead and open up our files, you know, why don't I just connect the SD card and you guys can see exactly what's on there. So we can connect up our SD card and we'll check out the files on there and we'll pick one of them to play. All right, so here you can see, as I said, I renamed it to Galaxy, and we've just got all of these files in here. So we're going to, let's just go ahead and try to play the hum sound. So we've got a sound at galaxy/hum/hum1.wave. So we can just type that in, galaxy, if I could type, /hum with a capital H, /hum with two M's, and it's actually hum1.wave. So this is the file that we're going to be trying to play, and we're just telling it to play that. And down here, what they've gone and done is they've gone ahead and added a serial input feature. So if the serial monitor is on, if we send the letter P in the serial monitor, then it'll play this track again. So that's actually pretty nice. It'll enable us to test it out pretty well. So if we get rid of our SD card and go ahead and connect it back up to our Arduino, and then we upload this code to our Arduino, we should be able to go ahead and hear that sound played. All right, so if I switch back over to the desk view, let me just go ahead and upload this, and then you guys should be able to hear the sound. Let me put my mic near that. Hopefully you guys can hear that. As you can see, it just went ahead and played that hum sound. Now the sound is like 8 seconds long, so it just went ahead and played it through once for us. But we obviously wanted to loop and play over and over again. So there's actually this feature, if we go ahead into the loop function, we can say if tmrpcm.isPlaying. And we want to say, put an exclamation point in here at the beginning. Exclamation point means not. So if the tmrpcm thing isn't playing a sound, then we want to go ahead and play this hum sound. So as soon as the hum sound ends, it won't be playing anymore. And obviously, and it'll go ahead and start playing the hum sound over again. So this will just loop our hum sound constantly, so we'll be playing forever. Now, obviously, we don't just want this hum sound. So this is pretty good as far as the speaker setup goes. We have an idea of how to play a sound, and we have an idea of how to loop this sound over and over again, which I just found by a quick Google search, by the way. So now that we have the sound worked out, let's go ahead and figure out another piece of the puzzle, and then we'll combine it together. Yeah, we can start with whichever one. Let's try the MPU 6050. So again, we have the Adafruit MPU 6050 library here. And if we just go to examples, we can look for MPU 6050. Adafruit MPU 6050. Sorry, there's a bunch of Adafruit ones. Let's try this basic readings one, see what's up with that. All right, so immediately we can see the baud rate is 115,200. So we will need to change to that in order for our Arduino computer to communicate. They need to be on the same baud rate so that they can understand each other. So once we are communicating with the Arduino and we open up the serial monitor, we will have to remember to change it to 115,200. So And if we forget that, then it'll just be a bunch of garbled characters down here. If you ever see garbled characters down here, it means you got the wrong baud rate. You just need to adjust it. Okay, so you can see it has some code here to make sure that the MPU 6050 starts up before we do anything. And it goes through some stuff to select which range and stuff you want. So like how sensitive you want it to be. And then here in the loop function, we have the good stuff. So you can see we go ahead and create a few variables here, and then we go ahead and use this function to fill out those variables with the readings from the sensor, which it says right here in this comment. So you can see we're printing out the acceleration on all 3 axes, the rotation on all 3 axes, and also the temperature, because for some reason the sensor has the temperature. We don't need the temperature. If you have some function on your lightsaber where you want to know the temperature, go ahead and throw that in, but I don't, so I'm just going to delete that, and then we can just go ahead and upload this to our Arduino, and we should be able to get out all of these values. So let's see what happens. Remember to change the baud rate, otherwise it'll look like that. Where is it? Here we go. All right, so you can see it's gone ahead and it started printing out. Here we go. We have the acceleration and the rotation. Now you guys won't be able to see this, but if I grab the accelerometer and turn it around, you guys, you should be able to see these numbers changing. There you go. So you can see they're changing all around just because I'm wiggling around the accelerometer. So if I rotate it, it'll be mostly rotation. Obviously, I have to move it, you know, because I'm a human, so it ends up moving a little bit. And if I shake it around, you should see the acceleration numbers change a bit more. So like the acceleration on the x-axis is getting up to, you know, 15 or 17 some of these times. And if we let it go, then it drops back down to something like 10 or something like that. So we can see the acceleration and the rotation are working. How do we actually use these to determine if our lightsaber is accelerating or if our lightsaber is rotating? All right, so the basic plan is this. If our lightsaber, we can combine all of the axes together to figure out the overall rotation or overall acceleration, because we don't really care what direction it's accelerating or rotating. We just care if it is, because if it is, that means we're swinging or we're clashing if it's just stopped. So what we're going to do is we're going to combine the accelerations and rotations. So if I just go ahead and create a float acceleration. We already used the word acceleration in there. Let's just call this all axes acceleration, Excel, just for short. And what we can do here is we can say a.acceleration.x, so the acceleration on the x-axis, and times a.acceleration.x. So what we've done here is we've squared it. So then also on the outside here, we're going to say math.sqrt, math.square root, the x. So if we just did this, we would get the absolute value of the x-axis. But we don't just want the x-axis, we want all 3 axes. So we're going to add them together. X times x plus y times y plus z times z. And if we add all these together and then square root it, we'll get just the overall acceleration across all of the axes. Now we can do the same thing for the rotation. So all axes rotation. I'll just do ROT for short. Math.square root. And this is, so we called the acceleration part A and the gyroscope part G. So A.acceleration, G.gyro. That sounds kind of nice. G.gyro.x times G.gyro.x, and then I'll just copy that and do it for the other 2 axes as well. All right, so once we have the overall rotation and the overall acceleration, we're going to use the rotation to detect swings, and we're going to use the acceleration to detect clashes. So this way, it's just more dynamic, I think. And so the rotation is pretty simple. We simply detect if the rotation is above a sufficient value, the overall rotation is above a sufficient value, then we're rotating enough that we want to call it a swing. And if the acceleration is a little bit more complicated. So for the acceleration, we want to detect if before we were accelerating really fast and now we're slowing down or inverting to the other direction. So the overall acceleration will decrease when we slow down very rapidly. So what we want to do is we want to store the last acceleration that we had and then check the current acceleration and see what the difference between them is. So if we go up to the top, I'm going to create a float last acceleration. And all we're going to do is we're going to check if all axes acceleration, let's check if last acceleration minus all axes acceleration is greater than 5. This is just as an example. So basically what we're, and then at the end here, we'll say last acceleration equals all axes acceleration. So every time when we finish the loop function, or before we print out all this nonsense, we're going to set the last acceleration to the current acceleration. And then the next time that we go through the loop function, we're going to say, hey, did we slow down by 5 from the last time we checked? So if we slowed down 5, whatever these units are, in between the last frame and this frame, that's very fast. So we've slowed down a really lot, which means that we probably hit something, and that caused us to slow down very rapidly. So we're going to qualify this as a clash. We're going to say serial.println clash. And like I said, the rotation swing thing is very similar. I don't want to call a clash and a swing at the same time, so I'm going to use an else if here. So if there's a clash, we'll do clash. Else if all axes rotation is greater than, and then we need to decide our minimum here. So we can see that the values here are pretty low. And let me shake it around a little and see what kinds of values we get. So because we're getting values under like 0.3 here. So if we shake it, we can see we're getting more like values, absolute values of up to something more like 2 or 3. So if this is greater than, remember it's all the axes combined. So let's do, I don't know, 3 sounds good. So if any of the axes are all the way at 3, or if 2 axes are at 1.5, then we'll trigger this rotation. And we'll run serial.println swing, because this is where we're detecting a swing. And then, yeah, for this, we play the swing sound and we play the clash sound. So the swing is going to get triggered a lot, because if someone just swings it back and forth, there's no clash, because it just gradually slows down as they swing it. But if they hit something, then there is a clash. So it could be like swing, 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 clash, right? There will always be a swing before the clash, but there won't always be a clash after the swing, because when we don't always hit something, we might whiff and miss. So I'm going to go ahead and upload this. Ooh, it looks like we have an error. So math, sorry, I wrote math.square root. It should, I believe, just be square root. I don't know why I put the word math before that. I was thinking like serial.println, but it's actually not that. It's just a built-in square root function, just like digital read or digital write. It's just straight up built in. You don't actually need to have, there's no object. It's just a straight up built-in function. So there's not much point in testing this. You guys are just gonna have to trust me that it works, and I'm not scamming you. You can see in the serial monitor, we can get some swings there and a clash if I crash it into the table. And yeah, it seems like it's working pretty well. So we've got the gyroscope down, we've got the sounds down. That's pretty much everything except for the lightsaber code that we already had before. So let's go ahead and do the new stuff. We'll combine the clashes, we'll combine the sounds and the gyroscope to get some cool sounds going, and then we'll bring in the LEDs code from the last one and combine it all together for our epic lightsaber. Okay, so we've got this program here. If we grab our other program somewhere in here, I think it's this one. Here we go. then we're going to want to combine them together. So I'm going to remove all these print statements here because we already know that the gyroscope works, so we don't need to be printing it out constantly. And I'm going to remove this delay at the end here. So all we're doing right now is getting the information about the sensors and then printing out clash or swing if it's a clash or swing. So then we want the hum sound to be constantly playing. So I'm just going to put that at the end of the loop function. If we're not playing the hum sound, play the hum sound. And actually it's not just if we're not playing the hum sound, play the hum sound, it's if we're playing nothing. So we're going to add a clash sound and a swing sound. And if we're playing clash or swing, this won't run. So it's not like the hum will just take over the clash or the swing. No, if we play a clash, then the hum will get canceled and it'll wait. And as soon as the clash is over, we'll go back to humming. Yeah, so let's just copy, and since the speaker code is shorter, I'm just going to copy that way over into the MPU 6050 file. Copying from the setup function, and we have all this stuff here which we don't really need. This is selecting this is basically just printing out what settings we have for sensitivity for the MPU 6050. When we say, hey, we want to do 8 Gs of sensitivity for the accelerometer, then it just goes ahead and prints that out as well, which is not really necessary. So we're going to keep these 3 functions here that say set accelerometer range, set gyros range, and set filter bandwidth, but we don't need to be printing out what we set it to because we know what we set it to, and it's not really important. But we do want to keep this code up here intact on lines 18 and 19 through 24, because this just checks if the MPU 6050 is actually working, and if it's not, then it'll say, hey, we couldn't find that. So we're not just trying to figure out forever what's wrong. We'll just immediately see that the MPU 6050 didn't show up. We also don't need this code. This is just an extra check if you're using one of the Arduino Leonardo or the Arduino Zero or something like that, then the stereo monitor might need to be checked if it's actually running. Okay, so we're gonna bring in these extra libraries and stack them up. Now I don't like that the chip select pin is mixed in with them, so I'm just going to move it to a separate area. I'm going to put these 2 objects together, just keep everything neat here. And I'm going to delete all these extra comments because I don't want them. They're just cluttering things up. Okay, so we got our libraries, we got our 2 objects, we defined our chip select pin, and we're holding, whatever the last acceleration was. We've successfully copied everything over. We just want to integrate it a little more. So we're constantly playing the hum sound. The next thing I'd like to do is go ahead and play the swing sound and the clash sound. We don't just want to play any swing sound and clash sound. We do actually. There's a few swing sounds and a few clash sounds, and we want to select randomly which one we're going to be using. So if I go ahead and open up my downloads folder once again and take a look at a copy of the files we have on our SD card, we can see in the clash sounds there's 3 different clashes to choose from. And in the swing sounds, there's 4 different swing sounds to choose from. Sorry, that's out of frame. So we just want to choose, and then you can see the folder names. For clash, it's just clash, but for swing, it's actually high swing. So we will need to change that as well. So here we want to say tmrpcm.play, and then it's going to be the Galaxy sound font because that's our sound font's name. And then we're going to Galaxy/high swing, that's the name of the folder, /swing, because they all start with swing. But then there's going to be a random number in here which will generate, and then it's going to end in .wav file because it's a .wav file. So plus, and then in between here we're going to say random, and then we'll put in the range. So in this case it's a random from 1 to 4. So let's just say the random generator did 1. It's going to be in the folder Galaxy/high swing/swing1.wave, which we'll find here. We rename this folder to Galaxy, so it's Galaxy/high swing/swing1.wave. And if it's any of the other numbers, it'll just be a different file. Now I actually did make a small mistake here. This should be up to 5 because the random actually excludes the last number. So if we say 1 to 5, it's actually 1 to 4. If we said 1 to 4, then it would only be 1 to 3. And obviously we want the 4th swing sound to be played sometimes. All right, so then we also want to do the same thing for the clash sounds, except that there's only 3 of them. And the folder names are slightly different. So if we just go ahead and paste this up here, we can say galaxy/clash random 1, 2, 3, just with 4, and .wave, and that'll just be clash 1, clash 2, or clash 3 .wave. All right, so now if we clash or if we swing, we'll play a sound for that, and we're just constantly playing the hum sound whenever we're not playing a different sound that'll override that sound. Seems pretty straightforward. Let's go ahead and try it out. Okay, so once our upload process is complete, our program is getting a little bigger, so it'll take a little longer, and we actually do have an error, so let me bring you guys back. All right, you guys can see it says invalid operands. We can't combine. It doesn't like that we're saying random 1, 4 and then just adding that to 2 strings. So I think what it wants is for us to turn these into strings first, these numbers, because remember, random 1 to 4 gives us a number. So we actually need a string. All right, it's not quite happy with that. It doesn't like that. So that's not exactly what it wanted. Oh, okay. So it automatically converted this to a string for us. That's not the issue. I was mistaken on that. What is the issue is I forgot to mention that the tmr_pcm.play function actually doesn't actually take in a string, it takes in a character array. Now, you might ask, well, a string is a character array, right? Yes, it is, but it also has some extra baggage on there, a couple of functions which make it easier to work with. So in order to turn it into a character array, since we're adding multiple together, we want to just combine them in parentheses. So inside these parentheses is going to be our string of all this combined. And then we're just saying string.c_str, and that'll turn it from a string into a character array. So all those strings get added, a string gets added to a number and another string, and it all comes out with one string. Then that string gets turned into a character array, which then the function will accept. Except if it doesn't, for whatever reason. It still doesn't like it. That was also not the solution. So I am probably being forgetful. Let me see what I did in this program at the very end. Don't look, guys, it's cheating. Well. We did tmr_pcm to play. Okay, I hope. Not sure exactly what we're doing wrong here. Because it looks pretty much the same to me. Let me see, maybe, and this is just, honestly guys, this is just what it looks like when I do my troubleshooting process. So maybe this will be a valuable learning experience. I don't know. So let me just try creating a string object right here. So I'm just trying stuff here, guys. String clash sound path, because this is the path to the clash sound that we've chosen, equals, and then I'm just going to bring all this stuff up here. So, and this way we know if the error isn't on this line but the string, then we know that we created the string successfully. And if it is on this next line, then we know, oh, it's something to do with this last part here, which is where I suspect it will be unless this solves the problem. Obviously, this thing here I didn't do anything about. Okay, so the error is up here, which means that it is something on this line. So there's something wrong on that line. It doesn't like one of these components. Now, a little trick here, if this works, which I believe it will, yeah, is we can actually just put enters here, and since we haven't given it a semicolon, it accepts that these are all the same statement. But since it's on 3 different lines, it'll tell us which part is the actual problem. So if you're ever adding some things together, whether it's numbers or strings, you can actually just use enter to separate them out onto different lines and find out which section is the problem. It's very handy. Okay, so we know the problem is right here with the plus dot wave and on the very end. That seems pretty normal to me. But maybe, I don't know, it doesn't, Okay, so it looks like it was the initial problem that I thought and the second problem that I thought both working together. So I unsolved when the first thing I said, if you remember, was, oh, it wants us to put string around this. And then I thought, oh, no, it doesn't want that. It wants something else. And so I deleted the string around that. It was actually both things at the same time. It needed both of those fixes. So I unfixed the first problem, which I had solved, and I rebroke it. So I went ahead and copied it down just so we don't make any further mistakes. And we just want to change the file path here. So if you guys remember, it was in the high swing folder. They're called swing, and it's random 1 to 5, so that we actually get 1 to 4. And just for the sake of neatness, I'm going to rename this from clash sound path to swing sound path. These are in 2 separate if statements, so they won't collide. The names won't collide, but I would like it to be neat, just so if anyone's looking over the code, they can understand it. All right, and just so you guys know, this is taking up a lot of space already. So we don't even have the LEDs code in, which is a big space taker upper, and this is already taking up like 70% of the project space, which is why I said you definitely need the Nano or a board with even more memory than that, because otherwise it's gonna get very tight memory-wise. Okay, so let's go back over to the desk now that that's successfully uploaded, and let's see if it can work. Okay. So if we power up our Arduino, it should start making the humming sound straight off, unless we made a mistake somewhere that that isn't a straight up error, so the compiler didn't catch it, which is always a possibility. All right, so I'm just re-uploading it right quick, just so you guys know. Since you can't see my screen, I'm just re-uploading it just to make sure that it uploaded. Just because I was having a couple of issues with that right before the stream. Okay, so that's let me just pause us for a second while I make sure that the code is uploading properly, and we'll be right back once it does. Okay guys, so yeah, it was not the Arduino IDE's fault, it was actually mine. I forgot this one very important line right here where we say TMR PCM.speaker pin equals 9. I forgot to set the speaker pin on the speaker driver, so it didn't know which port it was supposed to be playing the sound on. So yeah, copying and pasting can be dangerous because you can miss lines just like that. So yeah, that's all we have time for today. But we do have a pretty serviceable program here, which will give us our hum sound and give us our swing and clash sounds as well. But it's not yet combined with the LEDs that we had in our lightsaber before, which obviously are a necessity. So make sure you tune into our next live stream. Not sure exactly when it will be, but tune into that and stay aware of videos coming out so you can make sure to learn how to combine the LEDs from the last Saber and the sound and gyroscopes from this into one top of the line NeoPixel lightsaber. Thanks everyone for tuning in, and yeah, that's all for tonight.